Yeah, thank you very much, Marcus. So today I'm going to talk about a very basic question. And so I just have some measure space X, and I want to know what are all the compact operators on the corresponding L2 space. Okay, and well, there's a theorem you probably all know, at least for Rn. A subset of L2 is relatively compact if and only if it is bounded, it satisfies this equicontinuity condition, and it satisfies this condition, which is usually called tightness, and it just measures how fast your functions fall off as you go to infinity, right? And of course, I could apply this to an operator, and then I would get some characterization of compactness, right? And in fact, there is a pretty straightforward generalization for locally compact groups. You just replace what you would replace, right? Well, you have to take nets here, but otherwise it's more or less exactly the same, just what you would expect, right? But I actually prefer this symmetric version here. That's equivalent to the previous one, you see. So this is the same anyway, but this condition you can also write as that for epsilon there is a compactly supported G such that the supremum over F is less than epsilon, and similarly the third condition. And you will see later why I like this symmetric condition. But now, as I said, of course, you could now use this and get a characterization of compact operators. And well, now after almost 4 days of quantum harmonic analysis, you would probably all have a good guess what the operator version of this would look like. I'm not going to do that, but I will tell you in a second, in a simple example, why that's actually not what we want to do. It's not something, well, it's not something I consider useful. I will tell you why. But so let's go into a simple example. What's the simplest locally compact group? Let's say take the integers. So there, the L2 space is just the usual sequence space. And what's nice about it is that in this case, I can represent all my bounded operators as infinite matrices. Okay, I like matrices. I can look at the entries, very nice. Okay. So what happens for these matrices? Well, you can quite easily see that on L2, if you have this orthogonal projection on the entries from -n to n, then an operator is compact if and only if this limit here is 0. So essentially what you're doing is just you're cutting out the middle of the matrix and you let n go to infinity, and if this converges in norm, then you're compact. And it's easy to see, right? I mean, this operator is obviously compact. So if this limit is 0, then A is necessarily compact because, well, this is a finite rank operator. And the other way around, well, if A is compact, then since these Pn converge strongly to the identity, this will converge in norm to A. Okay, so really, really easy proof. And that's, well, in this simple case, that's the operator version of the previous theorem I showed you. And what I'm trying to tell you is this is just way too easy, right? This is basically just saying, well, to check whether my operator is compact, I just need to check whether it can be approximated by finite rank operators. That's not telling you anything, right? It doesn't help at all. And there's another point I want to make here. Namely, well, first of all, I can observe that, well, if my operator is compact, then, well, if I go along the main diagonal with my entries, then, well, I have to go to 0. That's exactly this picture I wanted to make. Well, right, if you cut it out, this needs to converge to 0. So if you just go along the diagonal with the entries, this needs to go to 0. Okay, and, well, of course, in any other direction as well. But the converse is wrong. Well, you could say, well, okay, I just went along the main diagonals, then, well, obviously it's wrong. I could just go in other directions. But no, even if I include all other directions, it's still wrong. This is a simple counterexample. So what do I do here? I put just 0 on the top left, and then I put A1, which is just 1 by 1 matrix 1, then A2, which is just 1/2, 1/2, 1/2, and so on. Put this in blocks, right? Put this in blocks. Then obviously, no matter in which direction you go, say from the origin, right, you will go to 0. But this is not compact. Why is this not compact? Well, these matrices always have norm 1. So no matter how much you cut out of your matrix, you still have something left with norm 1, so this will never converge to 0. Okay, so even if you have this in every direction you go to 0, it's not going to be compact. So that's why I'm saying this is not very useful. You can look at your matrix, you can know all the entries, everything goes to 0, but you're still not compact. So what do you do? Well, I claim that for a certain class of operators, this is actually sufficient. So I'm going to introduce a class of operators that I call band operators. So this is just what you would think they are. So again, this is just infinite matrix. Here you have some diagonals where you have some entries, whatever, and then outside you have only zeros. So it just looks like a band. That's why band operator. And then you just take the closure with respect to the operator norm, and well, I just call them band-dominated operators. Now they look something like this. Right? So just still goes to 0 as you go off the main diagonals, but there's no sharp boundary. Right. And now what's not so difficult to show is that, well, first of all, it's a C-star algebra, but also it contains all compact operators. And this is how a compact operator looks like in this picture, and maybe the picture already convinces you that this is band dominated. Okay, if not, then you have to check it by hand, but it's not so difficult. The point is, this is a good algebra to look for compact operators, right? Because it contains all of them, right? Okay, so let's see. As I claimed, there's now a theorem that tells you that, right? In this class, you have exactly this condition we had previously. We don't only have to go along this diagonal, right? And if this goes to 0 and your operator is of this form, then you're compact. And there are some other conditions. This one is the one where you can go in every direction, right? Which for non-band dominated operators doesn't work, as I just showed you, but this is just go in all directions. That's also equivalent. Or which maybe looks a little bit more familiar to you in quantum harmonic analysis, the shifted version of A goes to 0 in strong operator topology, and this should be plus and minus infinity. You have to go in both directions, just like here. Of course, that's the same, right? Shifting the matrix is just shifting it along the diagonal. So going, well, they have to show this, that it's the same strong operator topology and entry-wise, but otherwise it's the same, right? You just go to infinity along the diagonals. Okay, so I want now to talk about generalizations of this. So first and foremost, and most easily, I can generalize what a band-dominated operator is. Okay, this now looks a little bit complicated, but what you should have in mind is just this is a condition so that if you have a function that has support in some set, then you map it with A, then the support just gets slightly bigger, right? Gets only slightly bigger. Or in other words, if you have a set K and a set K prime over here, and if they far enough apart, they cannot communicate via A. Another way of looking at it. Okay? And if you're an integral operator, it's the same as before. It just looks like a band again. Right? Okay, so very, very simple. And again, take the closure, get a C-star algebra, contains all compact operators. Okay, so that's very straightforward. Now, okay, I want to discuss this theorem by Spakula and Willett from 2017. They generalized this from the integers to, well, pretty much any discrete metric space. I'm going to walk you through the different notions here. So strongly discrete just means that, well, the set of all possible distances between 2 points is also a discrete set. You take all possible distances between 2 points. This is a discrete set, and it's called strongly discrete. And bounded geometry means every ball of a fixed radius has only a bounded number of elements, right? So for every radius, there is an n such that every ball of that radius has at most n elements. That's bounded geometry. And now what's interesting is this property A. I'm going to explain to you in a second. That's really the interesting part, because, well, strongly discrete you can get rid of. That's not so important. That's just a technical thing you can get rid of. They even said that in the paper, but they just didn't want to make it more technical than it's anyway. So they assumed that, but said it's not important. It's not important. And the other thing is bounded geometry, and this is also needed because, well, if just think of a discrete, an infinite set with a discrete metric, then everything will be a bound dominated operator because everything has just distance 1. So, well, everything will be a bound operator, and then you can easily see that, well, the compactness criterion fails. Okay, so what's property A? Well, maybe before that I should maybe tell you there is a little bit of a caveat here, of course. If it's not a group, you have to explain what you exactly mean by shifting and so on. There is a way to do it. I don't want to get into technicalities. Just assume it's a group. Then this makes perfect sense. This also makes sense to just go a lot in a certain direction to infinity of whatever that is for your group. And this, of course, also makes sense. Okay, so what is property A? Property A is really a geometric restriction that comes from coarse geometry. And this was introduced by Yu in 2000, and I don't want you to look at it too closely, but well, he used it to show that, like, this implies coarse embeddability into Hilbert space, and this implies the strong Novikov conjecture, if that means anything to you. There are some connections, but it's not so important. What's important here, this somehow looks like an amenability condition, right? A little bit. No, this is not I'm not assuming it's a group, so it's not like an amenable group, but it looks kind of similar. But there is a different version that for us analysts, or some of us analysts at least, looks much better. It's something we know. So we say something has property A prime, and this is now not restricted to discrete spaces. If we have a partition of unity such that the diameters of the supports are bounded, then we have this sort of equicontinuity condition, right? And then we have this locally finite condition. So that just means if you take any ball, then the number of functions rho here you hit with your ball is always finite. It's a locally finite condition. And that's it. And in fact, in the discrete case, these are equivalent. Not so easy to see, but they're equivalent. And that's what we're working with. In fact, we defined that first because that's exactly what we needed. And then when we noticed later, well, that's just the same. But yeah. Okay. Good. What's also good here is, of course, now the geometric abstraction is, well, we now have it in a general metric space. We have a notion for it in the general metric space, and we expect that this is really needed for the theory to work. We want to have something analogous, right? Okay, good. So now let's move away from the discrete setting. And there are some problems. There are some obvious problems, right? We solved some, well, we generalized some things, right? Band-dominated operators and so on. But there's an obvious problem. Just take a function with compact support, take the multiplication operator. That's as banded as you can get, right? If you think of it, it's just, well, it's just one thing, main diagonal, right? If you want to think of it like that. And, well, but if you shift this to infinity, you get 0, right? Compact support, if you shift that to infinity, no matter in what sense it, well, you get 0, right? It's compact support. But obviously, this is not compact. Well, multiplication operators are very rarely compact, right? So, this just obviously doesn't work. Band-dominated operator goes to 0 as you shift it to infinity, but it's not compact. So if it doesn't work for this very simple thing, maybe everything is lost. Hold on. There's a possible solution. I'll tell you in a second why I call it possible. It's not what we want, but what we did in 2019, and we had something else in mind. So we cheated a little bit and said, well, okay, let's take a subspace, and just instead of operators on L2 space, consider operators on this subspace, and we choose the subspace in such a way that this gets compact, and then we somehow circumvented the problem, right? And well, that can be done, and this leads to this Fock space and Bergman space theory and so on. You can do that, and you get something. But obviously, well, I just changed the problem, so this is not what we want, right? It's not what we want. So I call this cheating. That's not what we want. So we need a new approach: quantum harmonic analysis. Great. So from now on, for simplicity, let's say X is a locally compact abelian group, so that I can define my shifts. So let's take the usual time frequency shifts here, as you all know them. And here I have some examples, like you had this the Pontryagin dual, so here you have the integers times the torus, you get the usual shift, except you also have this component here, which, well, is kind of important, and on the real line, you have this space factor. Okay? That's what we're all familiar with. And, well, now we can define this C1 algebra, where this shifting process is continuous in the norm topology. Okay? Sure, we've all seen that as well. And then Werner basically tells you via the correspondence theorem which operators are compact. Okay? So that works for any locally compact abelian group. Tells you essentially whether A is compact if and only if these shifted versions go to 0 in strong operator topology as you reach the boundary of this product. What I mean with the boundary, well, you take a compactification, and then that's the boundary of the compactification. In this case, it doesn't matter which one you take. Easiest probably take 1-point compactification, and then you just let those nets converge to that 1 point. Okay, but what does this have to do with what I told you previously? We now defined a whole different set. Well, in fact, we showed, together with Robert, that this is something we know, or, well, depends on where you come from. I come from this band-dominated theory kind of stuff, so that's something I know. It's actually the band-dominated operators intersected with, well, the band-dominated operators on dual. And you just map it back with the Fourier transform. So these are the same algebras. And so how much time do I have? Yeah, enough time. Okay, let me show you a quick sketch of the proof here. So in fact, we're not considering the whole C1 algebra. I'm just taking I said it the wrong way around. So it's a larger set. Yeah. So it's those which are continuous only in the second variable, and in the first one I just put the identity. And I show that this is exactly the band-dominated operators. And then via Pontryagin dual, I get this, right? So because for the dual, you just get to take it with the continuity with respect to the first one. Right? Okay, how do you do that? Quick sketch. Well, we know, again, from correspondence, this C1 algebra can be written as the set of all of these convolutions. But in fact, you can also write this thing as a set of all possible convolutions, with now this delta 0 tensor L1 function on the dual. Now you make a direct computation. You show that if you take something in here, that just looks like that. Ka is the integral kernel of A, can be a distribution, but doesn't matter. And then it's from this, well, you sort of have an integral operator. You just look at the kernel and you see this must be band dominated. So of course I'm skipping some details here. This has to be made precise, but just sketching. So it's what I'm saying is it's conceptually it's not that difficult. On the other hand, if I have a band operator, well, let's forget about the k here maybe. It means okay, I didn't define this properly. The k is a measure for how far these are apart or how wide the band is. Sorry about that. I messed up two different definitions. Anyway, point is, we now can write A again in this form, so one can show that we can find an L1 function here, so that A is just equal to this. So this convolution with this thing just does nothing. Essentially, you convolve with something that is on the band just one, and so it does just nothing, sort of. And then, well, you see it's of this form, so it must be in here. Okay. For details, I refer to the archive paper that appeared like 2 weeks ago. Okay, so what is the takeaway? So now we can characterize compact operators on arbitrary locally compact abelian groups, and we sort of have the same characterization as for the integers, right? So, well, this looks a little bit awful, but this is just saying that, again, if you think of an integral operator, the kernel goes to 0 in every possible direction, but you have to make sense of it with, because now you're not discrete, so you have to have to consider this weakly with some functions, let's say compact supporters. But that's morally, that's the saying that no possible direction, you go to 0. You can consider this in the weak operator topology as you shift to infinity. These shifts go to 0, either in weak or in strong operator topology, or, which is the one I prefer, again, symmetric. A is in here. Maybe I should have said that before, but that's just the Fourier transformed version of A is band dominated on G hat, and well, this goes to 0 as G goes to the boundary of G, and this goes to 0 as chi goes to the boundary of G hat. Again, you can choose strong operator topology or weak operator topology. Okay? So you see, very similar. Now, what if I go back and put a discrete group in there again? What happens? Do we reduce to the other case? And indeed, well, what happens is this is just everything. Like if G is discrete, G hat is compact. If your group is compact, band dominated is everything, right? And similarly, you would not get, let's see, you would not get this here because you don't have a boundary. Right? The boundary of a compact set in its compactification is just nothing. Right? So you get rid of this, and then you have the same as before. So the moral of the story is, in the discrete world, you don't see the Fourier side because everything's just trivial, right? On the other side, on the dual side, you just, in the discrete case, you have just trivial conditions. So that's why you don't see them if you just do discrete theory. So, but in the non-discrete world, you need them, as we've seen in this simple counterexample. Otherwise, it's just wrong. Now, one last thing. If you remember, I told you there was a geometric obstruction. Right? I told you there is this property A. So there's Spakula and Willett showed this can work if and only if your metric space has property A. If you plug in discrete space here, you don't see the property A. Why is that? Well, the thing is, we're now working on locally compact, and the keyword is abelian. This locally compact abelian group, these are amenable. And amenable implies this property A prime. And that's why you don't see it. Just all of them, all the locally compact abelian group satisfy this property. And that's why you don't see it. And well, random comment here as well, you can actually choose these row J's in S0. That's not so important if you're doing L2. Yes. But it's more interesting if you actually want to do this on modulation spaces. You can do that. There it's interesting. For L2, it's maybe not so. It's not important for the L2, but in the modulation spaces, it's kind of neat that you can choose them. Thank you very much.